ipTEST was the first company to introduce the concept of index parallel testing of all device parameters from a single manufacturer. Index parallel is a proven architecture for the fastest distributed device testing, whereby each test station around the device handler tests specific parameters of a device under test. For example, all the tests related to high voltage testing, like device breakdown and leakage, take place on one site with dedicated high voltage hardware. All the low voltage high current tests, like on-state resistance and peak current, happen on a different head with different hardware, and so on. ipTEST produces a wide range of generators designed to test low voltage and high voltage static parameters, as well as unclamped inductive load avalanche tests, gate resistance and capacitance, switching speed tests, and for packaged devices, forward bias die-attach tests. Our generators are flexible so that they can be reconfigured to perform sequential tests through a single set of contacts for wafer probing at up to 10 kV. ipTEST's established test system is MOSTRAC, which features flexible configurations and a wide variety of generator types. Our next generation test systems are called MOSTRAC 2 and represent a step up in terms of throughput, reliability and modularity. They feature high-speed Ethernet communications and digital control of the generator's internal control systems, as well as high-speed state machine-driven test execution, whilst maintaining backwards compatibility with test plans written for MOSTRAC using the same Linux-based controller and system software. MOSTRAC 2, or M2, has been designed to maximize throughput, increase productivity and protect users' existing hardware investment. All the measurement electronics have been housed in individual generator enclosures with a height of 470 mm and a depth of 500 mm, which is small enough to allow them to be attached directly to a handler table or mounted close to a prober card, ensuring that sensitive measurements can be taken as close as possible to the device under test. This is especially important when it comes to measuring switching tests like device turn-on and turn-off times and body diode recovery energy. The most important consideration when designing M2 was the need to maximize throughput. To help achieve this, we implemented Ethernet communications between each generator and the Linux host controller on a closed network which minimizes latency. We also moved to a new controller architecture using field programmable gate arrays, which uses a high-speed state machine to execute each particular test. As well as being able to control test execution to sub-microsecond resolution, it simplifies the way in which test modes are written by implementing each mode in tables within the FPGA. The benefit of this is that new test modes can be implemented faster and opens up the possibility for user programmable test modes in future. Another step towards improving throughput was to implement digital control of the internal feedback loops, which enables faster pulse rise times by being able to tailor each test individually within the test plan. Every test on M2 can also be captured in real time using the waveform capture facility for rapid plan development. Another key achievement is a step change in the confidence you can have of test results returned by M2. By using a stable internal reference on the main measurement board for HV and LV generators, M2 is able to self-calibrate and achieve a 0.1% accuracy on the main voltage and current measure ranges. Offset errors account for only 1 nanoamp across all current measure ranges, even down to the lowest 100 nanoamp range, leading to unparalleled confidence in measurements. Not only that, but M2 can measure force conditions for each test to the same accuracy, meaning that datalog files can contain results for both the measure and force conditions of each test without impacting on test time. M2 is designed to grow as a system as your test needs change. We use the same control card throughout all our M2 generators, and the HV and LV generators also share a common measure integrate board on which all the sensitive measurements and range switching takes place. It's also where most of the high voltage and high current electromechanical relays are situated. Boards occupy a fixed number of slots in an enclosure, and because of the common backplane architecture across all enclosure widths, it means boards can be placed in any slot. Enclosures are available with widths from 3 to 7 slots, which means a user can start with a simple high voltage or low voltage generator of 3 slots and expand up to a 7-slot HV and LV generator with up to 3 kV and 1000 amp capability. Not only that, but a system can be completely reconfigured to suit how your production mix changes over time without having to dispose of your initial M2 investment, saving money, time and the environment. If you'd like to learn more about ipTEST and our products, you can find more information by visiting our website at www.iptest.com. Thank you.